Good afternoon. Today we'll be presenting our product, Grapht. My name is Ricardo, this is Thomas, and as you can tell from our name, we have something to do with graphene. So I know many of you have heard of graphene. It has amazing mechanical properties, and because of these properties, everyone wants to put graphene into pretty much anything, everything. However, graphene doesn't really want to go into anything. There's tons of phase separation, dispersibility problems, and that's the problem we seek to solve. So one of the major markets where graphene would be used as an additive would be in advanced polymer compounds, engineering materials, where you want these material properties of tensile strength, in aerospace components, in automotive, in medical, flexible electronics, gaskets, O-rings, especially in dynamic sealing, various rubber products. And the addition of graphene or other additives increases the different material properties such as tensile strength, abrasion resistance, thermal conductivity, electric conductivity. Basically, almost any material property they can think of, there's some additive that can be used to change this property. And graphene itself has many of these different properties which it can actually help with. So graphene is very electrically conductive. It has amazing tensile properties around 130 gigapascals. It has good thermal conductivity, which helps in distributing heat during high performance uses. So that helps there's no hot spots and there's no failure points in the material. So due to this desire for companies and industry to try and integrate new graphene additives into their materials, and and it's a really big market. So currently we have like a $40 billion industry in terms of material enhancement additives, with expected growth to 60 billion in 5 years. And that's why we came up with Grapht. It's a polymer compatibilized graphene additive, which allows for ease of compounding, improves the dispersion of the graphene within the matrix, and also improves the transfer of the desirable graphene properties to the material.
So let's take a closer look at each of these points. When I'm talking about compounding ease, if you're wanting to add a carbon filler material to your polymer, as in carbon black, carbon nanotubes, or graphene, often you find it's in this powdered form that you get it. And now this powder is really awful to work with. If a little breeze or a little electricity, it'll fly up, it'll get into the air, you can breathe it in, and that's not good for your health. Additionally, when you're trying to weigh it out, it can be difficult to get the precise amount you want, and when you do, you take it over to your compounder and you spill a bit and you don't get quite what you want. With Grapht, we provide an easy solid or liquid additive. It's initially in a solid state, but with the addition of a small amount of solvent, which will evaporate during the compounding, it can be turned into a liquid. With this, there's no risk of aerosols forming or dust that you can inhale, and it makes it far easier to get the amount that you want in your compound at the beginning and through the end of the compounding process. Additionally, Grapht provides an improved dispersion homogeneity. With original graphene, when you put it into your compound, as Ricky said, it likes to clump to itself. It likes to stack up and form these agglomerated clusters. So you have to get some high shear mixing, a lot of energy put into there to try and break it up, and even that doesn't usually get it all the way dispersed. This can cause you to have to add more graphene than you wanted to, and that's expensive because graphene costs quite a lot. With Grapht, it's been compatibilized so it likes to be in the polymer. It disperses far more readily when you mix it, and this directly leads into the transfer of the graphene's amazing properties to your polymer matrix. Now, good homogeneity is important for almost all of your properties, especially mechanical properties such as your tensile strength, your shear strength, your abrasion resistance. But it's most important for conductivity properties such as your thermal and electrical conductivity. In order to get a sufficient conductivity through adding filler into your composite, you need to have enough of the filler to create what's called a percolation network that allows the conductivity to flow along the filler particles. Because Grapht is more easily dispersed in your composite, you get a higher effective concentration for the same weight loading, which allows you to achieve these conductivity values at a much lower original weight loading, keeping costs down. So how do we make Grapht? It's a very simple, very flexible process. We start with multi-walled carbon nanotubes, and then we use a chemical unzipping procedure using potassium permanganate and sulfuric acid to open these into graphene nanoribbons. These graphene oxide nanoribbons have many functional groups on them, and they don't quite have all the mechanical and electrical properties that we want from graphene, so we take a step to reduce them, which removes many of the oxide-containing groups, but leaves a lot of them along the exterior, which are then used for our functionalization. To attach the polymer, we purchase a short-length hydroxide-terminated polymer, and then we attach it using a diisocyanate molecule to create two urethane linkages. And this urethane chemistry provides a lot of flexibility in the opportunity because there's many polymers that have hydroxide-terminated forms available. So you can use a lot of different polymers and have this graft be compatible with all sorts of different polymers.
So for the production of Grapht, we decided to use carbon nanotube as a precursor rather than purchasing reduced graphene oxide or starting with graphene oxide from graphite sonication. One reason that we chose carbon nanotubes is, for one, the price of carbon nanotubes as opposed to graphene oxide. There's a huge discrepancy. Multi-walled CNTs are $4 a gram, while graphene oxide that's purchasable and usually used as an additive is $350 a gram. So from the get-go, we have huge cost savings in terms, especially if we want to scale up industrial use. On top of that, when you produce graphene oxide through the Hummers method using graphite and a sonicator, you're just hoping that flakes come out and go into the solution, and you have no control whatsoever upon the platelet size or the size distribution. But if you start with carbon nanotubes, you already know the diameter and the length of carbon nanotubes. So when you unzip these carbon nanotubes, you know the exact size of your graphene ribbons, which gives you another parameter to play with when you're optimizing mechanical properties. On top of that, carbon nanotubes are an old technology. We've been working with them for a couple decades now. And the scaling of the production of carbon nanotubes for mass production is readily available, which is why instead of going straight from graphene oxide as a precursor, we use carbon nanotubes. Because it's more control, it's cheaper, and there's the ability to scale up.
Additionally, we chose to use a Grapht 2 mechanic where pre-made polymer chains are attached to the substrate of interest instead of a Grapht from mechanic where you actually in situ polymerize the chains on your substrate for a number of reasons. The first reason is because Grapht from mechanics are hard. They're difficult to do. They have a lot of reagents, they have a lot of parameters, and batch-to-batch reliability can be different. A slight change can get you completely different results, or it might not work that time. Additionally, there's a lot of, as I said before, a lot of polymers freely available at low cost that work very well with the chemistry we were working with. Finally, for the polymer that we chose to use for our prototype, we chose to use poly-THF. And we chose poly-THF because it's a very common polymer. It's used very often in industry, and so it's already become very cheap because of its high production. It's easy to use because the molecular weight we chose has a melting point very close to room temperature, so it's easy to convert into a liquid, which is easier to work with. And it's quite safe. It doesn't have huge health risks associated with it, which I appreciated using it in the lab. Additionally, because it's so commonly used, there are many polyurethanes that are produced using poly-THF, which will allow Grapht as its prototype to be much more attractive to industrial users because it's already compatible with many of their currently produced products. Finally, very recently, BASF, the world's largest producer of chemicals, introduced a biologically based poly-THF, which will allow, in the future with future work, Grapht to be produced in a more green way. And since this is such a big movement now in almost everything, being able to produce our product in a green manner will open up further markets, and it looks good. People like it.
So following the production of our first prototype Grapht, we of course wanted to make sure that the material we're presenting you is the material that we're saying we have. So over here we have a few SEM images of the different stages of our Grapht manufacturing synthesis process. In the first image you can see our MWCNTs. They have a good size distribution with pretty much the same diameter across all the CNTs. And to the right of that, you can see our graphene oxide nanoribbons. This is following the KMnO4 H2SO4 unzipping process. As you can see, there's a change in morphology. It's no longer a tubular structure, but it looks more flattened. If you were to measure the width of the structures, you'd see that they're roughly equivalent to 100 nanometers, which would what you expect when you unravel our purchased MWCNTs. We then reduce these graphene oxide nanoribbons to get the reduced graphene oxide nanoribbons. Now, this image is somewhat strange because as you see, the morphology changed again to more of a nanotube-like structure. But this is easily explainable from the sample preparation process and the fact that the functional groups on the reduced graphene oxide nanoribbons would be concentrated around the edges because in fact they're less reactive than the surface sites. As the solvent evaporates, these hydrophilic functional groups tend to clump together, which would reclose, non-covalently of course, the graphene oxide nanoribbons. However, we can tell for sure that the unzipping occurred because if you look at the distribution sizes of the nanotube-like structures in this image, you can see that there are some structures which look like 10 nanometers across, which would indicate that the inner CNTs within the MWCNTs came out after the unzipping process has been exfoliated and are now back to these tube-like structures. And finally, we have an image of our graph, the poly-THF linked to the graphene oxide nanoribbon compound. We also did ATR-FTAR to make sure that the bonds and the graphene were adequately completed. So the the linkage and grafting reaction went well. The first peak that we'd like to look at is the diisocyanate peak, which as you note is not there, which is good. Diisocyanate on its own is somewhat of a health risk. But as you can see from our 2 graph samples, there's none left. That means that the diisocyanate was completely consumed during the reaction and attached to the functional groups on the reduced graphene oxide. We also look at the OH stretching and the C double bond O stretching, which would be more functional groups that we can attach more chemicals to. So it seems that diisocyanate may not have fully saturated all of the available functional groups on the reduced graphene oxide. However, this actually offers an interesting opportunity to further functionalize Grapht with other chemicals. For example, UV degradation is a big problem for sealing systems, and by adding UV-sensitive functional groups, it's possible to add further functionality to Grapht to increase the material property enhancement of this additive. And lastly, we have CH bonds at 2 peaks, which are very large after the addition of the graphene, the linkage of the graphene to the poly-THF, and this indicates that the graphene was well added to the mixture. We also tested the tensile properties of Grapht, not necessarily for the material properties of the additive itself, because frankly they're not that great, because there's short chain lengths and you don't really have that much entanglement. However, this test has managed to show that inter-batch variability is low. Our material properties between the multiple batches are nearly identical, which shows that our procedure works, it works repeatably, and we can do it multiple times. There are many directions which you can take Grapht. We have left many engineering levers and knobs which you can turn to optimize the future material properties and how Grapht interacts with the future polymer matrix. I mentioned a while ago that functionalized Grapht with the extra functional groups will allow for further functionality of this additive. Also, because we have graphene there as reduced graphene, we also have the chance to do conductivity studies by increasing the weight loading of the graphene within the Grapht additive itself. Once we reach percolation threshold, it may be possible to have some conductive polymer and maybe some sort of thin film conductive Grapht. Also, we need to do polymer matrix testing. So as Thomas mentioned earlier, because our reaction is so flexible, we can use almost any polymer that has hydroxytamidine end groups. We can choose different kinds of polymers to attach aside from poly-THF, so we can expand the market aside from polyurethanes to butadiene rubbers or nitriles to further increase material properties along those materials. Of course, process scale is a big thing. We think our process is very scalable. It's simple, it's flexible, and the technology is pretty old. And we would also like to look at changing the dimensions of the CNTs initially used, which is another parameter which can easily change. So one interesting thing about the CNTs, the graph that we were able to make was because we used such high aspect ratio CNTs, the material that we made is actually really flexible, which is unusual for graphene added polymer mixes. So in short, Grapht is cheaper, stronger, it's well dispersed. You can use Grapht to put graphene into nearly anything you want to think of because of the flexible reaction mechanism and because of graphene's really, really good material properties. We'd like to thank everyone on this slide, and thank you for listening, and we'd like to field any questions you might have.
So you started from multi-wall carbon tubes.
Yes.
You did the oxidation
Mhm.
reduction. So before you did the reduction, what color? I mean, it's black or it's
It was
Black.
it
It's
was
black.
blackish brown. It wasn't a deep dark black.
okay.
It was
So it's not black.
So the reason
It's not like a graphene.
Oh, so it is black. The reason it's darkish brown is because you have some aluminum oxide left over from the reduction
Mhm.
of the oxidation process. But if you apply more acid to that, it goes away, it becomes completely black. So it
Yeah.
is at that point it is graphene oxide.
Okay.
Yeah.
So then, I mean, you mean in the center of
Mhm.
this graphene is also get oxidized.
Yes, it
right?
should
Yes.
be.
Effect.
Hence the reduction.
So similar to the normal way to make
Mhm.
from a graphite,
Mhm.
it's lots of defects,
Yes.
outside and inside. Just the shape is different.
Yes.
You have controlled shape this time.
Okay. So what type of reducing agent?
We use
We-
hydrogen hydrate and ammonia.
What the
Hydrogen
Hydrogen-
hydrate plus ammonia.
hydrate?
yes,
Mm.
monohydrate,
Monohydrate.
Oh, okay.
So not as dangerous as
pure hydrazine.
But-
And we use that primarily because it's easier to use. There's also multiple studies that have been done with this where you use thermal reduction, and that works just as well.
Yeah. It's more just from a time perspective we
Yeah.
decide to use this.
So without the mineral oil, it's pure. So normally in the mineral oil, right?
Mhm.
So without the mineral oil.
Yeah, without the mineral.
Okay.
Just
It's
just
chemical.
yeah.
Mhm.
Yeah.
Yes.
So in terms of incorporating the poly-THF and isocyanate, do you just lump everything together? Or?
No, we start with the dispersed graphene nanoribbons, and then we add in the isocyanate. We allow that to react for a while so that statistically, for the most part, one of the isocyanates on that diisocyanate has reacted to the graphene. We will get a couple where the diisocyanate links between two graphene nanoribbons just because of statistics, but for the most part it's just an isocyanate on the graphene, and then we add the poly-THF after that's reacted.
Essentially, you're creating an isocyanate functionalized graphene.
Yeah, in a two-step process.
Just might not have an answer, but just for speculation. The big thing about carbon black is the filler is really cheap.
Yeah,
And
it is really cheap.
Property enhancements. So do you envisage the application where you can really compete with that aspect of carbon?
Probably not, because carbon black is amazingly cheap, and it does a decent job.
But
But
we do a better
for-
job with graphene.
Yeah,
And
graphene
more functionality.
provides a better job, although it's more applied to high-end products that where you'll pay a little bit more for a better product. So it's not going to be ubiquitous, but it will bring the price down from where it is right now.
For some applications, it will take the price.
Yeah.
I just wondered if you knew what was.
Yeah. But this is way cheaper than current graphene additives. Like
Yeah.
Yeah.
So, okay, I think that's the end of this session, and thank you to the two speakers and all other speakers, and thank you for your attention.
thank you.
Thank you.